Alright, in this video we're going to talk a little bit about continuous functions. What does it mean for a function to be continuous at a point? Well, I'm going to first give a definition that's kind of informal, but it's easy to understand. And then after that, I'll give a definition that's mathematically rigorous, but it'll require a little bit more explanation to understand what it means. So let me write that down. What does it mean for a function f of x to be continuous at some value a, at some value x equals a? Well, the informal definition that I'm going to give is as follows. If we look at the graph of f, and there's no breaks in the graph at x equals a, then that's what it means to be continuous, informally. So first of all, I should say first of all though, f of a has to be defined, right? And there are no breaks in the graph. I'm going to give some examples in a second, so if you're not sure what I mean when I say there's no breaks in the graph, don't worry, I'll do some examples in a second. So there's no breaks in the graph at the point a comma f of a. So what do I mean by this? Well, let's take a graph, and let's say this is the number a, okay? And here's our function. So this point right here, this y value would be f of a, right? So this point would be a comma f of a. So f of a is defined. If it wasn't defined, then what would happen? Well, there would be a little hole there, right? If f of a was not defined, it would look something like this, right? There'd be like an open hole there. But in the original graph I drew, it was solid. So that means that the function is defined there. And are there any breaks in the graph? No, there's not. It's nice. There's no jumps or anything like that. How about I do another example where, why don't I just move this over? Oh, that doesn't look good, eh? 1 second. Let me fix that. Sorry about this. Let me quickly fix this. I apologize. I think I've figured this out now. All right, sorry about that. What I was talking about a second ago was that this graph here, this graph is continuous at x equals a. So in this example, f is continuous at x equals a. Now what I want to do is another graph over here in which it is not continuous there. So let's do an example where we have a situation like this. Let's say A is right here this time. Maybe this is the way our graph looks this time. Just by looking at that, is this function going to be continuous at x equals a? Well, first of all, we need f of a to be defined. Is it true that f of a is defined? Yes, it is. Because, look right here, we have a solid dot. So f of a is actually this value over here on the y-axis. But there is a break in the graph, right? Because when I follow the graph here, I'm following along, and then when I hit A, I have to kind of lift my pen from the paper to continue tracing it out. And so we have a break in the graph here, so this function is not continuous. Can I just abbreviate it as CONT''S? That's just abbreviating continuous. So f is not continuous at x equals a in this particular example. All right, so I hope you see the difference between these two. Here we have a break in the graph, so it's not continuous. And here, there is no break, okay? And you know, if I did this little example as well, I know how to fix that now. If I do this example here, how about something like this? Let's look at this graph. Is f continuous at a in this example or not? Well, it's not, because since we have an open dot at f of a is not even defined here. So in this case, f is not continuous at x equals a. Now remember, a is just like any number, like 5 or -3 or whatever. I like to use letters because it keeps it general. So if the function's not even defined at the number, there's no way it can be continuous. I think that's worth writing down. So let me just say that right now. If the function, I already said it, I guess, but it's so easy to forget, and it's really important to remember that. So I'm just going to point it out again. If the function is not defined at x equals a, then most certainly it's not continuous there. Continuity demands that the function be defined at that number. So if that number a is not in the domain, in other words, the function is not defined there, then right away, you don't have to do anything else. F is not continuous at that value of a, at x equals a. Okay, so the function has to be defined, such as in these first two examples. And not only that, the graph cannot have a break, okay? If you have to draw the graph and lift your pen from the paper when you get to A, that's going to mean there's a break in the graph, and therefore it's not continuous there, okay? So that's the intuitive definition of continuity, that the function is defined at that point and there's no breaks in the graph. What I want to do in the next video is actually give a more precise definition using limits. And that's the real way of proving things are continuous or not. But I wanted to start off just by giving these informal examples. And really, if you understand how these examples work, you're going to have a really good idea of how what continuity means in general.